Hello, welcome back to parser hacking. We are working on a recursive descent parser, and I've already recorded a couple of videos about that. And so this will be, I believe, video number 3 or 2 if you're counting from 0. And tonight I want to work on Pratt parsing, which is to say operator precedence parsing, because I want to get it right from the beginning. I don't want to try to bolt it on later. I want to make sure I'm doing everything right from the start. And I've been, I should say Pratt Parsing is named after Vaughn Pratt, who created it, or wrote a paper in 1973, I believe, describing this parser. It didn't get a lot of recognition at the time, but people have picked it up since then. And so it's a really neat and elegant way to handle operator precedence. And I did look at the paper. I'm not really good at reading sort of heavy papers like that, but I've been reading this book, which I believe is backwards to you because of my webcam being flipped around for feng shui reasons. But I've been reading this book by Thorsten Ball, probably saying his name wrong. Sorry, Thorsten. Called Writing an Interpreter in Go. And he talks about the Pratt parsing technique and explains it very eloquently in Go. Now I'm not amazing at Go, but I could kind of pick up the syntax or the technique. And so what I wanted to do was translate that into Ruby so that I could really wrap my brain around it and hopefully explain it to you. And then what we want to do from here is to implement this in C++ in our parser. So translate this Ruby to C++ just by hand. And so I'm trying to think of how I should explain this. What is the best way? I'll go over the tests. Pratt parsing is basically taking a sequence of tokens and grouping them together based on their precedence. And it does it in a very eloquent way, like I said. And so I wrote some tests here to show what is happening. So if we have an integer token followed by a plus, followed by another integer, followed by a multiplication asterisk, followed by a third integer, we want them to be grouped like this in the comment that I've created over here. So we want 2 times 3 to happen first, and then the result of that will be added to 10, and the result should be 16. And so in the same way, we want this to happen here, but we want it to happen in reverse because the multiplication has swapped places with the addition. So we want it to happen in this order. So 10 times 2, the result of that added to 3, and we get 23. And so on and so forth. So I've just got a few of these. This less than is very similar. It's just another operation. And there's another less than, another less than. So obviously not all of the operators are here, but we can test the concept. And the magic of Pratt parsing is this precedence hierarchy of that we can compare later down. I'll show you how that works. But the lowest precedence is 1, and we can make these numbers whatever we want as long as they are different numbers and they're in the right order. And I specifically skipped 0 because I use 0 to indicate there's no token at all. So that's why there's no 0 here. But lowest is 1. Equality checking is a little bit higher than that. Less than or greater than is a little bit higher than that. Sum, and this includes addition and subtraction, is higher. Product, which includes multiplication and division, is higher. Prefix, which won't really get into much here, but like a prefix is like a not. It's like I say, not false would be true, right? That's a prefix operator, which means there's nothing on the left side. That's why it's called prefix. Another prefix operator is the minus. So if I have -3, then there's nothing on the left side, and that's all that there is to say about that. And then calls, method calls are 7. Now, we may have to tweak this to match Ruby, but this was out of the book, and it's probably pretty close. And then we have this map, a hash table, Now in C++, I don't know that I'll implement this as a hash table. It'll probably just be a switch statement. But in any case, this is the way to look up which precedence each of these operators gets. So equal gets the equality precedence, not equal gets equality, and so on and so forth. So plus and minus get sum, multiply and divide get product. And so I think that makes sense. And naturally, there'll be way more operators in here down the road, but this is just enough to prove the concept. And then we have this thing called null denotations, which that's from Vaughn Pratt's paper. That's what he called them. I think he had a shorter word for it. Don't remember what it was. But he called them null denotations, which are things that don't have anything to the left of them. And integers are in this pile of things. Also prefix operators, like I showed you, the not, like the exclamation point for negation, the minus sign for negative. So this list would grow as we have more things that nothing is on the left side, as opposed to left denotations where there is something on the left. And all of these are infix operators. Another one I believe would be like a plus plus. Ruby doesn't even have that. So like if I had I plus plus, that would be a left denotation. There would just be nothing on the right of it. There'd be nothing over here. That's an interesting thought. But anyway, so this just maps which method we want to call for various operators. And in all of these cases, we want to just treat this as an infix, meaning infix between two operators, or no, between two operands, an operator in the middle between two things, and that's what infix means. And if you already know all this, then I'm sorry for, I don't know who my audience is, but I'm really proud to have learned this, and so I want to share it with you. And let's see. So we have a list of tokens that's passed into our object. We can get the current token, and we can peek at the next token, and we can advance our cursor or index to the next token. Okay, so, and we're almost to the end. I mean, that's the bulk of the code is just in defining these maps of operators to precedences and stuff like that, and operators to method calls. And so we have our, let me start at the bottom here. We have two methods here. One is parse integer, which all it does is it grabs the literal from the token, and like down here where I have type integer and the literal is 10. It's going to grab that number out and advance the cursor and then return that integer. So very, very simple. Parse infix expression is accepting a left side. I just realized my left and right will be backwards also. Yeah. Anyway, a left-hand side operand or value. It's going to get the operator from the current token type. It's going to advance the cursor. It's going to then recursively call, and this is where the recursive dissonant parser comes in, parse expression. And it's going to pass in the map, the precedence of the current operator. And as we saw up here, that's one of these: equality, less, greater, sum, or product. And so it's essentially passing an integer, one of these integers, into parse expression. And then when it gets back, now I should say this parser just evaluates the result right away. It doesn't turn it into an abstract syntax tree. I just wanted to demonstrate the concept. And so what I'm doing is I'm just calling left.sendOp, which translates into left dot. Now if it was a plus, it would be dot plus like this, and then right, which in Ruby is the same as left plus right. And so we're just doing a little bit of metaprogramming here in Ruby to evaluate it right away and return the result. And so that's why when we do parse expression must equal 16 down here, we aren't getting an abstract syntax tree with, nested things. We're just getting the result right away. And that's fine, but that doesn't have any bearing on Pratt parsing at all. That's just what I chose to do. Okay, so that is out of the way. Let's get up here to the meat, and this is where the magic happens. This is so cool. We get the current token. We assume that there is a null denotation where we currently are, where our cursor currently is. Where for the current token, we assume there's a null denotation. Now, again, the null denotation is just a method that we can call that does not accept a left-hand side. In our case, the only one we support right now is parse integer. So this is going to get that parse integer function, stores it in fn, and then we call that function, which is what send does in Ruby. And the result is the left, and that's the new left-hand value that we're going to use. And so the beautiful part is in this while loop. So while we have a current token, assuming we haven't gone off the end, and while the precedence of the operation we're currently on, the one passed into parse expression, while that is less than the precedence of the operator we're about to process, then we want to keep going through this loop. And inside of the loop, we grab a left denotation, which in our case is a parse infix expression. That's the only one we have, parse infix expression. And we call that. We do a send with it, and we pass the left side into it. Now, that's the whole thing. That does the right thing with all these operators, and it's beautiful. So if I run this test, I have one test and 5 assertions and no errors, and it works beautifully. And so I want to try to show how this works. Let's see, it'll just call this debug, because I just want to run this one test right here, and let's just delete all this stuff. Oops, and delete all that stuff, and we'll just do a print. Oh, I don't want the value thing. So if we just run this, we get 16, right? What if I do this? Do I have enter? Oh, gotta install it. I love this tool. It's my best tool ever. If you don't use this tool, you need to use this tool because it's awesome. So what you do is you give it a list of files, and I guess I could just do echo, but anyway, and then you run entr, and I always do -c for clear, and then the command that you want it to run. And so every time that file changes, it's going to run our script. So we can just toggle back and forth really quick. And so what I want to show is kind of what's happening in this loop, this magical loop right here. So what if we did this? What if we print? This is going to be kind of janky, kind of some puts debugging here. And we print what the left is, what the precedence is, and then what the precedence will be for the next operator. And then I want to kind of do the same thing here, but I want to say this is like, whoops, this is when you exit the loop, the while loop. Precedence, What if there's no current token? We need to handle that. If there's no current token, then that. If there isn't, then a 0. If there is, then show that. Okay, I think that's it. So if I ran this, and we're on this expression here. So we have a 10 plus a 2 times a 3. And we want the 2 times 3 to happen first. So I want the 2 times 3 to happen first, even though we're scanning through the tokens linearly from left to right. So what does that mean? Would it be really cool? You know, I just had a thought. What if I put this inside a terminal inside of Vim? Whoa! Mind blown. Okay. So let's try. I want to try not to bore you to tears, and feel free to skip this if everything's already clear to you, but it wasn't to me, so I thought it might be helpful to go over this. So we're inside the loop. That's what this little arrow to the right means. We got a 10 for the left, which was this literal 10 here. Because remember, we did the left denotation. Let me scroll up just a little bit. The null denotation for this parse expression, that returned just the integer itself. And so we got a 10 for the left. And remember, we're printing the left value here. So we have a 10. You know what? I'm just going to take some time to say direction is in, left is this, precedence is this, and next precedence is this. I'm going to do that all the way through here just to make this a little bit easier to understand, hopefully. Cur token, and we're going to say 0. Okay, does that make it a little bit? Yeah, I like that better. Okay, so we're inside the loop. We got a 10. The precedence of the thing that just happened is 1. And the reason is because we're on lowest. And I should say that lowest is the default precedence. There's nothing lower than low, because right here we have the default precedence of lowest. And so the precedence of 1 is definitely less than precedence of 4. And 4 was the sum, the addition operator is a precedence of 4. So we're inside the loop. We grab the next, we grab the left denotation, which is a parse infix expression. We call that, which we'll go down here. It grabs the token, advances the cursor, and then it recursively calls parse expression with our current precedence, which is 4. Right here, this 4 came. Now we're back inside of this method and we're recursively inside of it. And so we're going to go inside this loop again. And 4 is less than 5. 4 is less than 5, and 5 is the product. Yeah, 5 is the product. So what that means is we're going to go through this loop and do everything again. And we're going to grab our left denotation, which is parse infix expression. We're going to call it, passing in the left-hand value, which is a 10. No, which is a 2, sorry, which is a 2. And then we're exiting the loop. So this is like returning back up the chain 3 times. And so you can kind of see, I don't know, I hope that makes sense. I don't know if it does or not, but it made sense to me the first time I looked at it. It's kind of fuzzy now, but so let's just go puzzle through this. So we have a 10, and then we're going to add 2 plus 3, which these two turn into a 6. 2, sorry, not 2 plus 3, 2 times 3. 2 times 3 turns into 6. And then we add the 10 plus the 6 and we get 16. I hope that makes sense. And now, so I guess the point is to recognize this pattern of it's going right, right, and then left, 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 which means inside the loop, and then return, return, return. Does that make sense? Probably not. Let's reverse these. So let's put the times first and the plus second. What's going to change over here on the left? It's going to get the 10 and go inside the loop. And then it's going to say, well, 5 is not less than 4, so we have to exit out of the loop. Like, we're done. We're going to we're going to evaluate this first part. We're done. The precedence is higher, meaning we need to stop. And so 10 times 2 is 20, and we pass the 20 into the next expression, which is the plus. And then we do plus 3, 20 plus 3 is 23. Well, now that I have thoroughly confused you, and I don't know if that helped at all. It helped me a lot. And I guess if none of that made sense, I just want to say that the beauty of Pratt parsing is this very elegant little loop right here of while there's a current token and while the precedence is less than the precedence of the next token we're processing, then you keep going and you keep evaluating that inner loop. And that's what allows us to treat a multiplication as a higher precedence than an addition, and so on and so forth. So I think that's enough about that. I do want to show you one other really cool thing about Pratt parsing, which is grouped expression. So let's say that it handles grouped expressions. And we're just going to grab this. And I'm just going to delete all this junk. And let's say this is a plus. Let's say this is a times and this is a plus. But we want to group. So really what we want is 3 times 1 plus 2 or something like that. So we want to evaluate the 1 plus 2 first to get 3, and then 3 times 3, even though this is normally not the order things would happen in, but since we've added parentheses, then that's the order we want them to happen in. So now if I just want to make sure that we get a different result. So 1 plus 2 is 3, 3 times 3 is 9. So this should be 9, right? And this is going to fail because we don't know how to do, actually I haven't even done what I want to do yet. I want a parens here and a parens here. Okay, so now that looks right, and now it'll fail for the reason that it didn't know what to do with this type of token. So I do want to make sure that if this wasn't here, what would be the answer? It would be 3. 1 times 3 is 3 plus 2 is 5. Okay, so if we get this wrong, then the answer will be 5. If we get it right, the answer is going to be 9. So the really cool thing, check this out, is that we don't have to do hardly anything. All we need to do is treat the parens as, the left parens that is, as another type of null denotation. We're going to parse a grouped expression. Parse grouped expression. And then we're going to add a new one down here. Def parse grouped expression, and that doesn't need anything because it's a null denotation. So we're going to call advance, and then we're going to do a expression equals parse expression, and we're going to pass in lowest. And we don't have to do this because that's my default, but I'm just going to do it to be explicit. And by doing this, by setting the precedence back to lowest, the grouped stuff just magically works. It's so cool. And so I am just going to throw in another thing here, say if, how am I going to do that? Yeah. Okay, if not cur token, then we're going to say raise expected but got EOF. And then else if cur token type is not equal to this, then we're going to say expected that but got cur token dot inspect, and then we're going to return the expression that we got. So that's it. Hopefully I did it right. Expected 9 got 12. What did I do wrong? Oh, I don't know how to add. I was doing multiplication. Yeah, so 1 plus 3 is 4 times 3 is 12. Yeah. And if this was not working, then the result would be 6 because it would be 3 times 1 plus 3. Okay, yeah. But, you know, once you actually figure out how to do some arithmetic, then it does work. And that is so elegant and so neat that I don't have to really do much at all. All I have to do is when I see the parens, I set the precedence back to lowest, and this magical little while loop does all the work. It's so great. This is my favorite new thing that I've learned in 2020. And 2020 is almost over. I've learned a lot this year, but this is one of my favorites. But anyway, that long introduction out of the way, now we get to try to build this in C++. So without further ado, let's close that and let's pull up our parser. And try to figure out how we're going to implement these things. I do not want to build a hash map for this thing. I think I'll just build some functions. So let's just say that we have a plain old enum. Maybe. Okay, so let's just have a plain old enum, not an enum class, because I want them to all be represented as integers. Yeah, so precedences equal, yeah, I think you do it like this. Been a while. And then we're going to say lowest equals 1. Can't I do this? Do I have to do a comma? Yeah. And we're just going to copy all these. Okay, so we're going to do that. And then we're going to say precedence map, but we're going to return, let's not make this, yeah, let's just make it singular. Precedence, it returns precedence. It's going to take a token. Parser token. Yes, I did mean Lexer token. Thank you very much. That might be the first time that's actually helped. And then we're going to say switch on the token.type case. Let's just do the ones we need right now. Let me go look at my Lexer because I don't actually remember my types now. Do I have a plus, right? Yeah, I have a plus. And I also have a minus and a multiply and a divide. Yeah. So we're going to say if it's Lexer, oh, this is going to be kind of long. Token type plus. Can't I do using? Sorry, this is me being kind of stupid, I'm sure, but can I do this? No. Okay, there's probably a shortcut. You guys, you're probably screaming at me to do some shortcut here, and I just don't know what it is. Why don't you like this? Oh, right. We're just gonna say that we have a default case to nat unreachable for now, and then if it's a plus or a minus, then we're going to return a precedence of sum. Return sum. Yeah, and then we're going to do multiply and divide. Divide as a product precedence. And that'll be enough to get started, I believe. Yeah, so that takes the place of this precedence map. We need some null denotations. I believe. I'll be right back. Okay, so we need something for this null denotations and left denotations. And I'm inclined to just do a big old switch statement as well. So let's say that we're going to return a node from, what do we want to call it? I mean, really like, I could have a pointer to, I mean, I've never done this, but I think you can have a pointer to a class method in C++. And so I could sort of mimic this, or I could use lambdas. You know, maybe I just use lambdas. So Okay, yeah. Another thing, sorry, I'm getting ahead of myself. Another thing that would be cool is instead of just grabbing the tokens here, it'd be cool if we had an M tokens down here. So be Elixir token. Actually, I believe it's a vector of tokens, and it would be M tokens. And this would be a star null putter. So what if we did that and we move this up to the constructor? Okay. Actually, we'll move this back down here. So this creates a new tree. We're going to loop through M tokens. That should all be the same. So I didn't break anything, right? Okay. Hopefully not. So now, can we have a node parse expression that mimics our Ruby parse expression? And it's going to take a precedence equals lowest. And I remember where I was going with this. I want this current token stuff. That's what I want. So let's make a private one. I'll say Elixir token cur token. I'm just going to spell it out. Current token returns M tokens. I think I have to dereference this. That means I also need an index. We'll say size t index is 0. Why are you yelling at me? M index. And we're going to set, well, we don't need to set. It's already set to 0. So that's the current token. And we want a peak token. It's going to be the, we probably need some ifs in here so that we know what's going to happen. So we say if M tokens dot size. So if we're at index 0, I would say if M index is less than the size, then do this. Otherwise, we want to return a Elixir token. What is, I've already forgotten. There's like a bad one. I thought there was a bad token. I'm not seeing it though. What did I call it? Invalid. Token type invalid. Okay. Be kind of cool if we could just say invalid here. Let's just go make it. Let's just go make that. Static, not satanic. Static invalid token. It's going to return a token with token type invalid. Did I do it right? Probably not. Probably need to move this down a little bit. That's everything inside of that. I really need to move some of this stuff out of the header. It's getting a little bit crazy. Actually, maybe that's what I want. Maybe I want it right here. I don't know, I'm just going to 0, 0 for now. Not sure what to do about that. Okay, so now we have this little convenience thing, and this is a pointer. And we're going to return an invalid token if that's not a good thing to do, if there is no current token. And then similarly for peak token, if +1 is less than, we're going to do +1, otherwise return an invalid. Okay, so now we have our current token and peak token. We don't have advance yet, so we'll do void advance. I'm going to say index ++. Yeah, that works for now. Okay, so now we've got all this code built. We don't have parse expression quite yet, but we'll work on it now. So we'll say if, actually no, we'll say token equals current token. And we're going to say let's do it as a lambda for now. Let's do it as a lambda. So we're going to say auto parse integer equals, I've kind of forgotten the syntax here, but I believe you do square brackets, and then this takes no parens, so we do something like that. And parse integer is just going to, well, we've already done this right here, haven't we? Is it just going to return this? Is it going to return a new literal node with an integer value? I think that is definitely possible. Definitely needs an environment. So we need an environment here, and we need to capture that here. And then also we need this, and we need current token. Okay, so that's what parse integer looks like. Oh, we didn't advance, so we'll say auto lit equals this, return lit, advance. So I don't know. I don't know if I love it being lambdas. I don't know. I might revisit that, but let's say it's going to be a lambda for now. Infix expression. And parse infix expression is going to take a left, and the left is going to be a node pointer. And let's just delete this and start over again. So the operator is the current token. And then we're going to call advance. We're going to advance past the operator. And then the right-hand side, we want to call parse expression again, passing the environment. And we want to get the precedence, so I'm going to call precedence for the operator. And then we want to, now here we were just evaluating and returning the actual result, but we want to build up a sort of node, a type of node we don't have yet. So in our current parser, the one we didn't write, what do you get if you do 1 + 1? What does it look like? It's a call with the receiver and then the symbol and then the argument. So it's a call. So I think we want to make a call node. So let's just put this here. Are these in alphabetical order? They are. So I'll just put call node here. Call node here. We're going to say receiver. message, and then let's just have one argument for now, just to make things simpler. And so let's see, what is our receiver? Oops. And we're going to say message. And Ruby method call is actually a message. It's called a message send. You're sending a message to the object. You can thank Smalltalk for that, I believe. And we're going to say argument. So now the receiver gets the receiver value. This is a comma. This is the message, comma, arg is the arg. And I like to assert these just to make sure I didn't miss something. Message, arg. Let's make sure we got something for all of those, even though the arg thing might not be right. But I think that's good enough for now. I don't want to do to Ruby yet. We'll just comment that out. We'll come back to that. This is a call node. So that's what a call node looks like. Now, how do we build a call node? We do it right here. We want to return a new call node, and we're going to give it three things. We're going to give it the receiver, which is left. And I believe already I've made a mistake. This is not a node. This is it a node? Yeah, it's a node. Yeah, I've made a mistake. So call node, it's not going to have values. It's going to be nodes, or at least the receiver's a node, and the argument's a node. Yeah. Did I do that right? Did I do it right? Actually, those are pointers. Silly me, silly me. Okay, those are definitely pointers. Okay. Yes. Hurts my brain. Okay. Now what are you complaining about? Variable precedence cannot be implicitly captured in a lambda with no captured default specified. Huh? Precedence? Variable precedence. It's not a variable, is it? Oh, aha. This needs to be get precedence. And we'll make this get precedence. Okay, so we want the receiver to be the left side. The message is going to be it's going to be a symbol value intern env, whatever the operator is, and the operator will be what? It's a token. It's a token. And it's going to have a literal. Yeah, let's just do that. So op.literal. And then the argument is going to be the right. Maybe? Oh, this is why I wrote this in Ruby first, because my brain thinks in Ruby, not in C++. Okay. So now we get to implement this. Now that we've built these lambdas, we built one for parse integer, parse infix expression. We're not doing grouped stuff right now. So we want to get, how are we going to do it? How are we going to do it? Okay. Null function. I'm trying to avoid creating this big old map here, because I don't want a hash map in my parser. Don't want hash map lookups. I still don't have. I'm just gonna make another lambda out of it. So null denotation for a Elixir token type. What am I doing here? This is I'm gonna say yes. Just realized I could put these lambdas inside of this lambda, but that would be really weird. I'm not really happy with this at all, but I'm just gonna keep going with it for now. Let's just return parse integer for now, because that's all we care about. And then we need one for left denotation, and we're going to return parse infix. Okay, so left function equals null, not left, how about null function? Null denotation, and we're going to pass in the token.type. And we're going to call, so I'm going to say auto left equals null function. I'm going to call it with nothing. Yes? Yes. We're going to call it with nothing. Okay, Elixir token. Can even get rid of that temporary variable because we don't need it. And now we get to do our while loop. While there's a current token, while its type is not equal to Elixir token, actually let's just say is valid. Yep. And the precedence that was passed in is less than get precedence for the current token. And I'm going to change this to be type. I want to change this to be a token type, so we don't have to pass in stuff we don't actually need. Type. There. Okay, so get precedence, we do it here, type, get precedence, current token, type. So while that's true, we're going to do something. We're going to say auto left function equals left denotation. And it's going to also take a token type, so it's current token type. And then we're going to say left equals left function passing in the left value. Cool. What did I do wrong? Parse integer. Okay. What? Incompatible pointer types assigning to a literal node star from a call node star. Okay, but I believe this is just a node star. Does that fix that? And this is a pointer. Type. Oh, I don't need the type. Current token is valid. And then we're going to return left. Oof. Okay. And I broke my cardinal rule. I didn't write a test first. I think I had in my mind that I had these tests to work with, but I don't. That was in the Ruby example code. So before we run any tests, let's go, before we save any of that code, let's go write a test. So I believe this right here is close to what we need. What if we just comment out all of those and we just see if it can parse 1 plus 3. And we'll do make and then Natalie test, Natalie parser test. I'm gonna move my Pratt thing somewhere else. Okay, and let's git stash that. And let's save this. Yes, I want to write it. And run this again. And hopefully we don't get a compile error. We get a test failure. Panic unreachable. Panic unreachable. Ah, that's fine. I think. Because this, our old code doesn't know what to do with that. Okay, very good. So now let's do git stash pop. That's fine. Okay. So here we are. Yes. Hopefully I didn't lose anything. If I lost anything, I'm going to be so sad. Okay, it looks right. Okay. Now it's still going to fail for the exact same reason because I haven't wired in that function. Okay, exact same reason. Exactly what I thought. I think I want to replace this. We're going to have to comment out our parsing strings because we didn't write that code yet. I will just comment that right here. So tree is going to return parse expression with the environment. And this is something we'll need to add later. Well, that's a cool thing. Interesting. Let's just focus this one test. And let's run it through GDB. I just want to see what is our stack? What does it look like? Symbol intern, line 135, we're creating a symbol. 135. Op literal is possibly null. Let's just do assert opt.literal. shouldn't be a null, and let's go ahead and printf it. Literal equals this might be a long video. Sorry about that. Thought things would go a little faster, of course. Yeah, so it's null. Why is it null? Why is it null? Okay, let's do this. We say to Ruby, and we pass in the environment. And then we can call inspect on that. What is the operator token? Oh, right. There is no literal. I knew that. Let's do type to S. I'll just say type cster. Return. Actually, I'm already doing the intern here in this giant switch statement. But I hate to call this toRuby method. I hate to call this toRuby method because I only made this for testing. And I don't want to use it internally because I think it'll slow things down because it builds up a bunch of objects. But I could why don't I steal out the switch statement, delete that, paste it here, and then return these. All the way down to here. Substitute type equals return space. Okay, and then the breaks can go away. Okay. You're not gonna just yeah, but it doesn't return that, it returns a value. Okay, so now we have this type thing. It returns the symbol. And what we were trying to do here was say value type equals type, pass in the environment. Now it's not going to like using the same name, the type, I guess. The type. Okay, so now we have a way to get this symbol out and without calling toRuby, so we can call type, pass in the environment. Actually, that's just the printf, so don't care about that. This is going to be type, and we don't want symbol intern in there either because it's already going to be interned. Okay. Why not? What's wrong? Why don't you like that? Give me a better error, please. No matching function call for call node, and then all the parameters. That's a value pointer, a node pointer, value pointer, node pointer. Candidate. No conversion of argument 2 from token type to value star. What? Oh, right, because I didn't pass in the environment, so it's the wrong type. Yeah, that's confusing. That's confusing. We'll say this is a value type value, which means I can go down here and change the type back to type value, type, and this is going to be type value. Okay, now are you happy? No. 263. 263. What's wrong now? Control reaches end of non-void function. Well, it shouldn't. It absolutely shouldn't. That should have been every case. I don't know. I'm sure the compiler is smarter than me. Boop, 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 boop. Are we going to get a seg fault? Oh, we got a nil. This is great. Never been so happy to see a nil. Okay, why did we get a nil though? Why did we get a nil? So let's go look at our parse expression function here. In a lambda, if you call return, you're just returning from the lambda, right? I'm gonna say yeah. Printf left equals left to Ruby environment inspect environment. Are we even getting this far? We are. We got a 1 and a 3. That's amazing. Oh, I know why. Right here. This is the default 2 Ruby. We did not create a 2 Ruby for our call node. This is so cool. We're getting so close. I want to indent this. So, okay. We have a call. And we want the receiver to be next. What? A receiver? And we want to call to Ruby on that. And then we want the message to be next. You know what I just realized? We want this to be a node. Why didn't I? Okay. We're making this a node. We're making it a node. Because it just makes sense to be symmetrical. 2 Ruby, we call it 2 Ruby here. And then the argument, we call 2 Ruby here. I'll need another closing one, yada, yada, yada. Okay. And then with call node, when we create it down here, oh, that's why. Well, I'm just going to do that. And if it's an operator, gotta save that. Okay, why aren't you, what are you worried about now? No matching. Okay. What did I do wrong? Node pointer, node pointer, node pointer, no conversion of argument 2 from token to node. Oh, it's a token. we need a node for the symbol. Right, I keep mixing up tokens and nodes. Tokens and nodes. Do I just make it a symbol node? Why not? We make it a symbol node. Symbol node. Symbol node. Yeah. It's a literal. It's another lit. Oh my. Lit. Cool. And we'll just do a new symbol node and type value. Maybe. Maybe it's right. Call lit1 plus lit3, call lit1 plus lit3. Okay, what did I do wrong? Oh, it's not a block. It's not a block. Oops. It's not a block because we deleted all that code. Okay. Well, what if we say tree equals new block node, and we return the tree, and we do tree add node, like so. Does that fix it? This is a little bit janky, but we're trying to get our test to pass, and it doesn't pass. No, it does not pass. Call. Now, there is a difference between the array syntax versus the S expression. That should be fine. They should be equivalent. What if I missed? A block inside of that is a call. We have a lit 1 followed by, oh, a lit plus. Interesting. Okay. So I don't actually want, yeah, this stinks. Okay, so I don't actually want this to be a symbol right here. I just want this to be, I want this to be a type value, which means I need to go back up here and say this is a value. Message is also a value because it's not a node. It's just not a node. Man, that's really ugly. Thank you. Thank you, auto formatting code. You really just won't let me do that? Ugh. Well, I'd rather have it on one line then. That's gross. Oh, it's so gross. Fine. Fine. Have it your way. Yes! It passes. It passes. Oh, I'm so excited. Okay, what if we don't focus that test? Do our other tests pass? Probably not. I probably broke them. Ooh. So the empty program is now failing. The empty program is now failing? Whoa, that's pretty wild. What does that mean? So down here in our tree, oh my goodness, this header is getting way too big. Down here in our tree, we always call add node parse expression. But what if parse expression returns what? What did it return? I don't know. I don't even know what that returned. let's just printf that. Expression to Ruby environment inspect environment. What are we getting during the empty? I probably should have focused that. We're getting a lit 0. What? Why? Why would we get a literal 0? Okay, so let's go up here to parse expression, and let's print the left value here. Left. What is that getting? I assume it's a lit 0. Yes. Yes, it is. Left is lit 0. And then there's no tokens left, so we just return that. But why? Okay, so let's just puzzle this out. If it's a null denotation, we always return parse integer. But what if there is nothing? Why don't we just say if current token for now, because, what do you mean? Oh, if it's valid. Oh, come on. I know I'm getting sleepy, but does that make sense? Because I thought in Lexer HPP we have valid somewhere. Is valid. Oh, is valid. Yeah, I'm getting sleepy, so things are coming a little bit too slowly now. But we're going to power through it. We're going to get all our tests to pass. Maybe not the string one, but at least these. Okay, so now this one should pass. That one, not sure because it has a new line. This one should pass, and that one should pass, I hope. If we did it right. Boom! Boom! No parens yet, no parens. No strings, no parens. We'll work on that next. Not tonight though, tired. Ah, it's so great. So we did break string parsing. Let's just look real quick. What would it take to parse strings? It would be a null denotation. It'd be another null denotation. And we would need our first, let's just add everything to the index in case I screw something up, which I do a lot. We're going to say auto parse string. Why am I typing this? Auto lit equals this. Current token literal, so on and so forth. We're going to advance the cursor, return lit, and that's a parse string. That's how parse string works. And now we need this null denotation. We're going to say switch on the type case. I've already forgotten the types that we have. I assume I have integer here, and then we have string. Yeah. Integer and string. So let's say if it's a Elixir token type integer, again, if you know a way for me to shorten that, Oh, I can do using, right? Using, I don't know. It's been a while. Type equals Elixir token type. Can I do that? Oh, I think I can. Okay. 68 enumeration values. I'm going to say string, and I'm going to say default is not unreachable for now, because we don't want that to, we want it to yell loudly. Okay, and this is going to be parse string. Variable parse string cannot be implicitly captured in a lambda with no captured default. Oh, yeah, I don't know. I can do an ampersand right here, right? No. Return type must match previous return type. Oh, no. Oh, I can't do that because they're different types. Of course. Of course. What if... What if this is a standard function? I think I can do functional or something like that. Maybe it's not... What? Okay. What if that's what it returns? Ugh, I gotta look up how that works. Gotta look it up. I think I can do that. C plus standard function, functional. What happened to my next thing? Weird. Standard function is a general purpose. Oh, right, because I have to do the return type and then the argument types. I knew that. So I need the return type is going to be a node pointer, and the argument type is, oh, it's variable argument types. No. There's no arguments. No arguments. Null denotation. No viable conversion from lambda. What if I say auto here and I do something like that? Does that work? Does that fix it? I think that fixes it. Do I even need these parens? Yeah. Gotta have the parens. Okay, null denotation. We might as well do the same thing over here. But this is going to return a, it's going to have an argument. It's going to be a, what is it going to be? It's going to be a node pointer. Nope, not that one. This one right here. Node pointer argument type. So does that fix strings? Or at least the ones that we had in our last video. Oh, it works. It works. So now we have everything we had in our last video, plus we have operator precedence parsing, at least for, we have, oh, let me just turn on Do Not Disturb for an hour. Okay. We have everything we had last night in our last night's video of parsing strings and numbers and an empty program, but we also have operator calls. Yeah, that's fine. Operator method calls, operator stuff, and it does operator precedence properly. So these two right here are very different. No, these are the same, but this one and this one is very different. The grouping is different. Yeah. Oh, that's so cool. That's so great. Takes a little longer to compile. I've noticed that when I include stuff from like functional, I include stuff from the standard template library, compilation takes a little bit longer. And I'm not married to this. Like series of lambdas that I'm using. Really not in love with that. I might play around with method pointers and see if that's a viable option. I think it'll be easier to read because we won't have all this nesting within one function. But I haven't done it before, so I've only read about it. I'm not even sure what the syntax looks like. So I will look into that, and maybe I'll work on that. But in any case, everything works, and we're going to commit this, and I'm going to say implement Pratt Parsing for operator Precedence. I'm throwing a smiley on there. All our tests passed. This looks great. We didn't break anything else, and we implemented a Pratt Parser. Huge thanks to Thorsten Ball. I know this is backwards. Sorry about my camera. Thanks to Thorsten Ball for writing this book and explaining it in a way that some very not bright person like me could figure it out. And I learned a lot, and I'm just stoked that I was able to get that to work, even though not completely happy with how some of the code turned out. It works, and we have a green passing test now that we can start doing refactoring. And I'll save that for maybe off video time, or maybe even in the next video. But in any case, we'll do it tonight. Thanks for hanging out with me in this very long video. Sorry it was long, but I think this is a valuable topic to sort of demonstrate, and hopefully it's helpful to someone. And if you made it this far, then congratulations. I think this is my longest video yet. Thanks for hanging out with me, and thanks as always for the encouragement and helpful tips and tricks that you might have. And if you want to help out with Natalie, let me know. And I guess that's it. So thanks for being here, and I'll see you next time.